What's up, ladies and gentlemen? AP Physics, once again to the Simpkins Physics Corner. Today it's WPE, work, power, energy. These are all of the concepts or the equations that are covered in this unit. So we've looked a little bit about what work is. If not, go back and look at the Introduction to Energy lesson, FD cosine theta. And today we're going to get into a little bit of the path independence of work. We're going to look at some examples of kinds of energy that we might see. And we will then later down the road get into the rest of those ideas. So here's your little conceptual framework for where we're going. First, let's recap what is work. All right, let's see if you remember, when work is done, energy changes is the big idea. When work is done, energy changes. Now, not the amount of energy, but what form it's in. So for example, if I have a suitcase down here very low, and then I lift the suitcase up, down here when it is low, it does not have a very large height or a large vertical position. And so its gravitational potential energy, which is determined by mg delta y, it's not going to be a whole lot of potential energy. In other words, if I lift something up a little bit and drop it on your foot, it's not going to do much work on your foot. It's not going to hurt that much. But if I lift it up, how would I lift it up? With a force over a displacement. And if I consider the angle between those two, that angle would be 0 degrees. Cosine of theta would be 1. And so FD equals W, or the work is equal to the force times the displacement. They're both in the same direction. So what does this mean? This means that as I'm doing work, I am giving more energy, or I am storing more energy, gravitationally speaking, in that object. Now if I drop it on your foot, wow, that's going to hurt a lot. So when work is done, energy changes. Now, where did that energy come from? Well, it came from the chemical energy stored in my muscles to lift it up. So you can't get energy for free. The energy was converted by the process of work from chemical potential energy stored inside my cells to gravitational potential energy stored as we lift the box up high. So we've already learned that work is a force over a distance. It's when, and work occurs, or work is an energy transfer that occurs when a force acts on an object that causes its motion. Now, when we're looking at work, we do the units of joules. And no, not that joule, but James Prescott joule. That's this guy right here, slightly updated for modern standards here. But work is a scalar, which means it doesn't have a direction. So it's not like I did 9 joules of work northeast. That's not a thing. But work is measured in joules, and just so you know, a joule is a Newton meter. So you might hear me say Newton meter, you might hear me say joule. Both of those are units for work, which is WD cosine theta. All right. So as we covered in our introductory lesson, if there's no movement, there's no work done. The work is always done parallel to the direction of movement, which we account for with the cosine thing, and only the component of the force in the direction of the displacement does the work. Component of the force. Vectors, trig, components. I see how this comes together now. Very good. So what about positive or negative work? Now, although work doesn't have it's not a vector, it doesn't have direction as far as northeast or things like that, we can do positive and negative work. Are we adding more energy into the system or taking more energy out of the system? Depending on how we define our system as we do this work. So if we consider the maximum amount of work done, it would be a scenario like this, where you have a force and a displacement in the exact same direction. And why is that the maximum amount of work done? Because when you look at the equation, FD cosine theta, if it's 0 degrees, and it's 0 degrees because both of these are pointing in the same direction, there's no angle difference between the directions of the force and displacement. That is why that's the maximum amount of work you can do. Let's say you're mowing the grass. So you kind of push down and forwards, right? Like your force is kind of down and forwards. You'd be doing less work than the first scenario, right? But you'd still be doing some work, and we would account for that with the cosine. Now, what about this? Let's say you're real, not the brightest tool in the shed, but you do get the lawnmower out of the shed, and you just stand on top of it in hopes that it will go that way, okay? Probably not going to be super successful at that. No work is done by that force because it's not causing that displacement. All right, now, but we also can have negative work. All right, this is a little bit of a weird idea, but it makes sense if you consider the equation we're using. FD cosine theta. What's the cosine here? Well, one of them's that way, and the other vector is that way. How many degrees is that? Oh, that's 180 degrees. Do you guys know what happens when you put 180 degrees in a cosine function? You get -1, and that's why you get negative work. And all that means is that we're taking energy out of the closed system that we've defined by some external force or work. So when work is done, energy changes. That's the big idea for the whole unit. When work is done, energy changes. What kinds of energy are we talking about? Well, if you see this term mechanical energy, there are two branches of mechanical energy, at least the main types that we focus on, and those are kinetic energy and potential energy. So kinetic energy has its own equation, potential energy has its own equation, and under potential energy, that means stored energy, we have elastic potential energy. So if I compress a spring, I'm storing energy in a spring. And then gravitational potential energy would be like if I lift something up off the ground, that I did work against gravity, and if I let it go, gravity is going to do work on that object. So that's how we store that gravitationally. So in order to assess a situation, a word problem, a lab scenario, ask yourself the following questions. All right, is it moving? If the answer is yes, it has kinetic energy. Is a spring stretched or compressed? If the answer is yes, then you have EPE, or they call it US on our equation sheet for U meaning potential energy. Don't get me started on that one. And S meaning of a spring. So if a spring is stretched or compressed, then yes, you do have potential energy as far as elastic goes. And if the answer to the question of can it fall is yes, then you have gravitational potential energy. Of course, if you're on the ground, you can't fall, so you have no GPE. So there you go. So let's look at some examples of work. There's me in my younger days, as I used to hit the plates a little bit more often. If I lift up a book, is that doing work? Yeah, of course, because my force causes a displacement in the direction of the motion here, and it causes a change in energy. How about if I push a cart across the table? If I push the cart, I am exerting a force, the cart's moving in that direction, and what kind of energy would we have? Well, this would be doing positive work because I would be increasing the kinetic energy of the cart as it moves faster. What if I launch something? All right. Well, here at the before scenario, we have US, we have elastic potential energy as we store energy in those stretchy bands. And then when I release it, that stretchy band energy is going to be converted by the process of work being done by the bands and the slingshot pushing on the book. It's going to launch the thing and convert the potential spring energy, or in this case, the elastic potential energy, into kinetic energy, because the thing will be going shoo and flying across. All right. What about if I slide something? All right. Now, here's an interesting one. If I slide a book across the floor and let it go, so I'm not touching it anymore, the book is moving this way, but what do we expect the book to do if it slides across the floor? Don't we expect it to slow down? Because the force of friction opposes motion. And consider the direction of these two things. They are opposite. Cosine of 180 is -1. So that would be an example of negative work. And if you think about this, it makes sense. The book has kinetic energy. Friction is doing negative work on the book. And what does that mean? That means that that energy is being taken away from the system of the book. And so that's why it eventually slows down and stops. Now, if you say, Mr. Simpkins, I thought energy couldn't be created or destroyed. Where did that energy go? Well, the bottom of the book and the surface of the floor will probably be a little bit warmer, and we'll have heard some sound. So thermal energy and this sound energy is going to be where that energy is what's called dissipated into the environment around it. Finally, if you bounce something up and down, all right, well, we have the force of gravity like this, and we'd have the force of the spring going like that. And of course, we'd be doing work because, as you can imagine, this would be boing, boing, going back up and down. As it goes lower, the GPE would decrease. But as it goes lower, the spring is stretching more. So we're going to either be storing lots of energy in our spring and a little bit of energy in UG, gravitational potential energy. Or if we go all the way up to the top, we're going to have more UG now, right? Because we can fall further. But the spring will be more relaxed. And so we'll have less US, or less spring potential. So there are some examples of work and positive and negative work. Now, let's get this principle down. The work done on an object is independent of the path, meaning it doesn't matter how you get there. It just matters where you started and where you finish. So if we take two movers here, one a little bit more stronger than the other, and one of them pushes their trunk up the ramp, okay, and then this guy comes along and he just lifts it up and just places it in the truck. You notice the difference here, right? In one case, the weaker guy would have to push with a force over a distance, but they would have to do it over a greater distance. This is why we use ramps and simple machines to aid us in the work that we do. The point of a simple machine is to extend the distance that we're applying the force, right? So that we don't have to apply as much force. Think of it this way. Instead of just lifting it up, 1 meter, I can push it over a distance of 2 meters. And now there's some trig involved with that, but you can see that it would require more force to just lift it straight up and put it in the back than it would to push it up the ramp or use that simple machine surface there. In both cases, the suitcase started on the ground and ended up in the truck. So it doesn't matter if I just lift it straight up and put it in there, or if I take this long ramp, this long path up there. The work done on an object is independent of the path. All right. And the thing about simple machines, just a little side note, they don't change the amount of work done. They change the way that the work is done. All right. So if W equals FD, consider this for a second. For the lift, the straight lift, the W that we do, it's going to require a big force over a small distance, right? Because I'm just heaving it right up. And the ramp, same size W, but it's going to require a smaller force, but the trade-off is over a greater distance. So in both scenarios, we get from the floor, or I should say from the ground into the truck, right? But in the lift scenario, we're required to have more force over a smaller distance. And in the ramp scenario, we have more distance with a smaller force. So here are your essentials. You can pause the video right now. This is just a little summary of what we've been over so far. To record your notes, I want to take a look at some examples after you copy these down. Let's take a look at one. All right, we got Diane, it's just like my aunt, pulls the sled, all right, and let's do a little speed reading here. The total mass of Jasper in the sled is 26 kilograms. The cord makes a 20-degree angle with the ground. As a simplified model, assume the force of friction on the sled is determined by UK. By the way, UK means kinetic coefficient of friction, which is the friction that we experience as two surfaces move relative towards one another, aka our sliding. Okay, here's it. Find the work done by Diane and the work done by the ground on the sled while the sled moves 120 meters along the path at a constant. Constant. Okay. Now, here's a little recap. Whenever we see the word constant, that's why I emphasize it so well. The word constant means that the forces, excuse me, are all balanced. We are in equilibrium if we're moving at a constant speed. Let me move myself over here. What that means is the pulling force. Did they give us the pulling force? Nope. That's fantastic. Didn't give us the pulling force, but it did give us some other information. All right. Let's see what we do know. We know that there's a 20-degree angle here. We know that our pulling force is going to have an X component, which has to be equal to the force of friction. Why? Because we're going at a constant speed. So force of friction equals the X component of our pulling force. Let me write that expression over here. F equals Fx, which means that mu Fn, that's the equation for friction, by the way, is going to be equal to F cosine of theta. All right, so I'll just drop that there as we start to unpack this one. Yeah, you know what? Not too bad, because it says that the force of gravity, well, it doesn't say, but the force of gravity we know is down, from normal force is up, and we know that those two forces are equal because we are neither moving up a hill nor down the hill nor accelerating up or down. We're in vertical equilibrium. And that means that Fn is equal to mg, which I can plug into my magic calculator to get an answer for the force of gravity and thus the normal force. So let's go ahead and do that quickly here. The normal force, sorry about that, go back. The normal force N would be 26 times 9.8, 254.8 newtons. All right, so I'm going to take that, and oh my goodness, we also know the mu, don't we? We know the mu is 0.16, okay? So let's go ahead and plug everything into our expression over here. 0.16 times the normal force, which happens to be 254.8, equals F times cosine of 20 degrees. All right, so now that we have this established here, we know what our force is, we can figure out how much work Diane is doing on the sled. So I'm going to take my magic calculator here and drop my numbers in, and whoosh, we got the force. The force is 43.38 newtons that Diane is pulling with, all right? Now, let's see. It says the work done by Diane. Now, here's the thing, all right? So Diane's force is actually this way. That's the one we solved for, is the overall force. And so if we look at the work done by Diane, it would be represented by FD cosine of theta. And so the force here would be 43.38 newtons. The distance, it said she pulled for 120 meters. And we do have to account for the difference in direction between the applied force and the displacement that's occurring. So 43.38 times 120 times cosine of 20 is going to be 4,891 newtons. I'm rounding it off a little bit. Now, here's the thing. Did we speed up? No. So kinetic energy did not change. Did we come up the ground or go into the ground? No. Is there a spring anywhere? No. So the energy didn't change. And what does that mean? When it asks us for the work done by the ground on the sled, that means the work done by Diane this way, kind of, and the work done by the sled must be equal. Why? Because the overall work done on this thing is 0. How do I know that? I know that because When work is done, energy changes, and our energy didn't change at all. Hey, check out the next part of this video coming up soon.